This year our team also related to water quality and biochar application. As the pathway of the organic and nutrient entering to surface water come from natural and human activities. To know the wastewater characteristics and control of water pollution to the receiving water is very important for aquaculture ecosystem, which reserve us as a food. So we extend the knowledge on wastewater characteristics and water quality management, particularly the water management from South Korea and Bangkok, Thailand. We are honored to have 4 speakers to share their experience on this issue this morning. We have 3 sessions related to water quality for aquaculture production, biochar characterization, and also use of biochar as an absorbent and nutrient recovery. On behalf of organizing committee, thank you for keynote speaker, presenters, young staff and students of the Division of Environmental Technology and all participants for coming and make this workshop possible. Your comment, involvement and expertise will make a productive workshop. Thank you very much.
Okay, and welcome again. Thank you, Dr. Soydoa, and welcome again for the guest speaker. The first speaker is Professor Dr. David Werner. He will address about the overview of the water, food, energy nexus and the role of the biochar. He is a reader in the School of the Civil Engineering and Geoscience in the Newcastle University in the United Kingdom, and he has an undergraduate degree in the environmental science with a specialization in the chemistry with from the ETH Zurich, and obtained a PhD degree in the environmental science from the Eco-Polytechnic Federal Lausanne. And he worked for 2 years as a postdoc at the Stanford University in the United States. And his group in the Newcastle University performed the research in the environmental engineering with a focus on modeling and the fate and remediation of the organic pollutant in natural and engineering systems for the optimization of the water, soils and sediment treatment designs. And his research stands on the include of the use of the metal impregnant magnetic and or reactive solvent for the water treatment, the use of the passive sample for the environmental monitoring, and the use of the enzyme in the wastewater treatment and the protection of water resource from the poison and the diffuse pollution. And he also interested in the reducing water and related energy uses in the built environment. As an environmental engineering master degree program director, he is currently responsible for the quality management and enhancement and standard of a well-respected program which has been running since 1963. And please welcome Dr. David Werner for the speaker.
For your kind introduction. It's really a pleasure to be back after a year and have this second workshop where you will later, or maybe I talk to this. Can you hear me? All right? Okay. So anyway, it's a pleasure to be back, and later in this workshop some of the students and postdocs will present the research that we did together with KMUTT. So to start the workshop, I just wanted to give a little bit of an introduction into why what we were doing here is so important, not just for Thailand and the UK, but also globally. So let me just briefly tell you a little bit about Newcastle University. So let's see if I can... Okay. So it's a relatively old university, although not the oldest one in the United Kingdom, but it has some famous alumni, such as Dr. John Snow, who discovered the cholera, or the link between water and the cholera. So there are some famous alumni from this university. We have some old buildings, and nowadays we have about 25,000 students at Newcastle University. And about 1 in 4 students is international, so we've got students from all over the world, including from Thailand, and I've got one student with me who's doing the MSc currently, for example. In terms of our income, we earn about £400 million each year as study fees and research grants, and about a fourth of our income is for research. So we are quite a research-intensive university. You already gave a very kind introduction of my background, but here's a little bit more about myself. I'm from Switzerland. So this is not proper British English that you're hearing today. It's my Swiss-German English. But I've been at Newcastle University since 2004, so that's 14 years now, quite a long time. And I'm a reader in environmental systems modeling. So these are the projects that I currently have, which are funded. So we have a project to work with India on vulnerability assessment and sustainable solutions for water quality management in the urban environment. So that's with IIT Gandhinagar in India. We've got a collaboration with partners in Africa to develop technology for surveying waterborne hazards, so water quality focus. And then we've got this project here that's going to be discussed today, which is valorization of agricultural wastes in the Thai rural economy for bioenergy production, nutrient recycling and water pollution control. And then I've got an industrially funded project which looks at macromolecule biopesticides in soils. So here are some of the people that work with me. You will later hear Dr. Wojciech Mroczki present his work on this project. So he's an environmental chemist. I also have an environmental microbiologist working with me on water quality. And then I've got a geoinformatician who helps us produce maps that allow us to illustrate spatially water quality in Africa. And I've got a number of PhD students. So one of them works on biopesticides. One looks at water use in the built environment. I've got a student that looks at biochar and using it for cleaning stormwater. And I've got a Chinese student that looks also at biochar, but how you can use it to increase carbon storage in soils. So there's some students that do similar work to what we will be hearing today. Then Playmart is an MSc student who's here with us today. So she just sits in the back if you want to wave at everyone. She's just starting research, but she will look at using biochar to treat digestate, anaerobic digestate from pig slurries. So if you are interested in that topic, you can discuss with her. And then I've got a student looking at pesticide sorption by activated carbon and also at water quality again. So just very briefly a slide about the work we do in Africa. So what we do there is we look at water quality, so groundwater that people use for drinking. And what we try to develop are methods to look at water quality that you can take with you if you go to Africa. So things that we can put in our suitcase. We go anywhere in the world, we set up our own laboratory, and it allows us to measure water quality. So for instance, what we see here is the MinION. That's a very small device for looking at bacteria in water. So we are working on developing this as an assessment tool. And photospectrometry, this is also portable, allows us to measure water quality. So what we try and do is, instead of taking the water sample to the laboratory and measuring it in the laboratory, we try and take the laboratory to the field and measure water quality directly where we take the sample. And the advantage of this is, if you work in remote places such as rural Thailand, but also in Africa, of course, this might be the better approach. You immediately get your results as soon as you take your water sample. And we try and put in a funding proposal actually to try and do this also with KMUTT, develop this technology to assess water quality in agriculture. So hopefully we can get this funded and then we can continue our collaboration. That would be really exciting. But we don't just do this, also we develop software, and that's where the geoinformatics comes into play, that as soon as you measure data, you can upload it into the cloud and immediately display it on the internet. So as soon as you make a measurement, you can see what the results look like. And not just you can see it, everyone else can see it as well. So as soon as you measure, the people that are interested in your measurement will immediately have access to your data. And that's what we try in terms of digital technology. We try and assure that as soon as we make our measurements, we upload it through the internet. We have some algorithms that tell us whether the data is correct or if it's suspicious. So if there's a mistake, we can measure again. And then we also we map the data, we visualize it, we make it accessible to the end users. So yesterday we were on a farm, and the farmer showed us some lab results that he got from the government about his water quality. But he said there's no information about what he should do if the quality is not what it should be. So maybe this kind of approach where you would have an internet site where the farmer actually could see, if I have too much ammonia, what should I do? Maybe that would be a good way of improving the feedback from the people who do the measurement to the people who need to know what the data looks like and what it means. So that's just the background. Now this project that we have here, that we talk about today, is what we call a small-scale Southeast Asia Award. And the purpose of this was to establish collaboration between the United Kingdom and Southeast Asian researchers such as Thailand. So we gain competitiveness in gaining more funding for future research. And I think we've achieved this because we got to work together and we got to know each other and know each other's problems better. And what we are doing right now is we try and get more funding, including from the Newton Fund. So if we are doing this, we are doing exactly what this funding was meant to achieve. So hopefully we can not just have a good project here, but also continue our collaboration. Okay, so what this is focused on is on the food-water-energy nexus. And what, maybe you're familiar with this, but I'm going to repeat it again. So currently, if we produce food, we use a lot of water and fertilizer to produce food. If we produce fertilizer, chemical fertilizer, we use a lot of energy. If we treat water, we use a lot of energy. But also, if we generate energy, we also use a lot of water. So there's this negative interdependency where we use a lot of everything. We use a lot of water, a lot of energy, and both for our food production, but also to provide people with drinking water. This has a lot of impacts, so it means that we don't have enough water, or we don't have enough clean water, and it also means that we produce too much CO2, so it leads to global warming and so forth. And I'll illustrate this a little bit. So in the United Kingdom, this is the amount of water that we abstract from groundwater, surface water every year to provide people with mainly drinking water, so the public water supply, about 225 liters per person and day. And this is the amount of energy that we need to provide this water. So we need 8 terawatt hours of electricity to provide the water and to treat the wastewater. That's about the same as the output of a big coal-fired power station or a nuclear power plant. So we need all of the energy of a nuclear power plant in the United Kingdom just to provide water and treat wastewater. The technologies that we use to treat wastewater and drinking water are about 100 years old. So activated sludge, the system that we use in the United Kingdom, in America and so forth, was invented by British engineers 100 years ago. So very old technology. It works, but it uses a lot of energy. That's what I just illustrated to you. Now let's look at this globally. So globally, nowadays, 71% of the global population have safely managed drinking. Safely managed sanitation. So on the wastewater side, we still have a lot of need to increase this safely managed sanitation. So from 40% to 100%, 60% need safely managed wastewater management. Even if you have safely managed sanitation services, such as sewer, normally the water is not treated, so we don't treat the wastewater. So only 27% of the water that's connected to a sewer is currently treated. That means 73% of wastewater globally still needs to be treated if we want to have good environmental protection. Now let's think what that means in terms of energy. If we take the solution we have in the United Kingdom and we implement this across the world so that the whole population has the same type of water services that we have in the 116.7 terawatt hours of energy just for water treatment. That is more electricity than is being used in Africa. So all the electricity that we produce in Africa, if you want to use our wastewater treatment methods globally, we need it just to provide water treatment. Very clearly this will not work. It's not possible. We cannot implement the technologies that we have in the United Kingdom across the globe. It's going to use way too much energy. So we need to think again. We need to have better ways of managing water. Here's another issue. I told you how much water we abstract in the United Kingdom. But what's shown here is how much water we actually need to provide the United Kingdom. And this is what we call the water that's embedded in food and goods, or the hidden water demand. So we need about 10 to 20 times more water for our food and goods than what we abstract in the United Kingdom for the public supply. If your country on this map is red, and you can see that the United Kingdom is a dark red color, it means that we are importing a lot of hidden water from other countries across the globe. So the hidden water demand in the United Kingdom is 50 to 100 million cubic meters a year. And you can see that Thailand, for example, is in green. So Thailand is a country that exports water, hidden water. It means that some of the hidden water from our food is coming from Thailand. And a good example for this are shrimps, because if you buy shrimps in the United Kingdom, they will come from Thailand. So we don't grow our own shrimp, we grow shrimps that come from Thailand, and that's why our country is red, because the water that you guys use to grow the shrimp in Thailand is needed so that we can eat the shrimp in the United Kingdom. So that's also a big problem. So if everyone living on the planet had the same hidden water demand that we have, we would need about 7,600 billion cubic meters of water a year, globally. And that's more than the entire groundwater volumes in the world. And so again, if we continue like this, if we just want to use our model and have the whole world have the same approach, it's not sustainable. So for that reason, by 2025, it is estimated that half of the world's population will have water stress, not enough water to meet the people's need. So we need to think again, we need to do better, we need to have new ways of going about providing people with water and food. So one problem if the food is not just water but also fertilizer. So to produce fertilizer we use about 1 to 2% of the annual global electricity production as well. That's also not sustainable. Okay, these are the problems. Now I'm going to talk a little bit about solutions. Because people sometimes think, oh, the problem is so big we can't do anything about it. But that's not my attitude. My attitude is we can do something, we can change it, we can do better. And I will give you a few examples. I don't think there's a single solution, but I think there's a lot of small solutions. And I think today we will hear about a lot of small things that people try and do a little bit better. And if we add it all up, it can really make a big difference. So here's, for example, what we try and do at Newcastle University. In the United Kingdom, we have this league of UK universities ranked according to ethical and environmental performance. So our university wants to have very good environmental performance so that we have a good ranking in this league table. And you can see how we improved our position thanks to these efforts. So we used to be 104, now we are 8, 2017. How did we achieve this? So here's an example. This is the water that the university uses per person as a function of time, and you can see how this trend is going down. So at Newcastle University we use a lot less water now than in the past. It's a 40% reduction in water use. So very significant. I think if we continue like this, and the university still works, still functions, we still have a good university, but we use a lot less water. So some of the ways how we can achieve this, so we have buildings that use rainwater to flush the toilets, for example, so that reduces water use. And we also use some innovative toilets. So this toilet here is a propeller toilet, and it uses only 1.5 liters of water to flush it. If you have a good conventional toilet, you use 6 liters. So if you go from 6 liters to 1.5 liters, that's 60% water saving. You can still flush your toilet, you have the same comfort, but you use 60% less water. So these are some of the ways of how you can reduce the water demand and still have the same quality of life. The other thing we try and do is reduce wastage. So all the water that we just waste without really making good use of it, if we can cut this out, then without losing quality of life, we can use less water. And this is a perfect example for this. So we now monitor in each building how much water we use in each building in the university. Now you've seen this building here, which uses rainwater. So we thought this is a very sustainable building until we started monitoring how much water it actually uses. When we started monitoring how much water this building uses, we had this pattern here. So the minimum flow into this building always, even at night if nobody's in the building, even at Christmas when there's holidays, was always 1,600 liters per hour until they fixed the leak. So here they fixed the leak in the pipe down to 0. Okay? So we estimate that in the university, before we started addressing this problem, we lose about 30% of the water that's being supplied to the university just due to leakage. So it's leaking the pipes and dripping taps and running toilets. Very significant. That water is just wasted. There's no benefit from it. So if we can cut this out, we can very significantly bring down the water wastage. And we don't just reduce water wastage and the energy we need to produce that water, but we also have been changing the energy mix in the United Kingdom. So the energy that we need to provide the electricity for the water treatment looks very different nowadays from what it used to look like. So in 1940, 90% of the electricity in the United Kingdom was from coal. Thermal power has a very, very high embedded water demand. Just 2 years ago, for the first time, wind farms, so wind turbines, across the UK generated more electricity than coal power. A wind farm doesn't have a water demand. You don't need water to produce electricity with wind farms. So in addition to using less energy because we use less water, the electricity that we use to treat the water needs less water too. So we all of a sudden have these win-win-win situations where you have a gain here that leads to another gain and then another gain. So I think if we do more of this, we can have a much more sustainable model that will allow the world to have a good quality of life, but also with less environmental impacts. So we talked about food, and also in food I think we need to move to a more sustainable model of how we provide our food, with less water, with less fertilizer, with less energy. So we were at the farm yesterday where they grow this shrimp that we use in the United Kingdom. So if you people can produce the shrimp more sustainably, then we in the UK benefit because we have a lower imported hidden water demand. So that shows that there's a need for global collaboration on these issues, and you can see us at the farm engaging with the farmer and trying to understand how the production works and how we can make it more sustainable. So this is our project. It's about agricultural wastes and how we can, instead of having it as waste, how we can make use of it. And the idea is we can use it for bioenergy, for nutrient recycling, but also to address water pollution in agriculture. And that's the concept that's behind the research that we do. So instead of saying we need to produce food, we need a lot of energy, for example, we say, okay, we produce food, but as a byproduct of the food production we have some waste materials, biomass. So we use that waste from the agriculture to produce energy, renewable energy. And then we use renewable energy as well as the byproducts, maybe the biochar, to treat water. And then we have more water, more clean water that we can use again in irrigation and so forth. So we try and move from a model where you have a lose-lose-lose situation, that if you produce food you need a lot of water, you need a lot of energy. We want the win-win situation where from your food production you can produce energy and you can produce materials to treat your water. So I'm not going to show you the results because I think the students should be showing you the results, and you will see the results from the students later today. So I hope you will all attend these presentations and hear from them. But I'll just briefly summarize what we did. So first of all, we looked at the water quality and see what the main problems could be. So we looked at canal and pond water and sediment samples from 3 different sites. We looked at nutrients, BOD, coliforms, but also pesticides and antibiotics in these samples. So we will hear more about this in the afternoon. These are the materials that we looked at as potential agricultural wastes that we could use for biochar production. So we looked at coconut husk, coconut shell, corn cob and rice straw. We looked at different production methods. So we looked at relatively simple methods. Here, rice straw in a drum kiln at Kasame University. And then here you've got a traditional charcoal making by a farmer. But we also have this pyrolysis system that we use to produce biochar. And here's an example of the biochar that we produce from coconut husk. And then we looked at these potential applications of the biochar as a biofuel in briquettes, and I think there will be a presentation about this later, whether that might be feasible. We looked whether the biochar can be used to clean water, so we'll have a presentation on that. And we looked whether the biochar can be used to harvest nutrients and then apply this in agriculture as a soil improver. And again, there will be presentations on this topic. Okay, so I hope with this introduction you will be motivated to sit through the scientific presentations from our staff and students, and I'm really looking forward to it myself, but that's what I had to say.
Thank you very much, Dr. David, for the presentation. And for the second speaker, Professor Dr. Chungbuk from the Department of the Urban Engineering. And Professor Ha is President of the Korean Society of Environmental Engineers. His expertise on the environmental engineering in the term of water quality, GIS, applications in the water quality management, water quality modeling in the river watershed. And he got a bachelor degree in the civil engineer and the master degree from the environmental engineering from the Inha University in Korea. And he got a doctoral degree in the environmental engineering from the Osaka University in Japan. And right now, please welcome Professor Ha for the presentation.
Thank you very much. I'm very honored to have this opportunity to talk with you all. And then my bigger size, water and energy and food nexuses. Okay. From this one is from the hydrology issues. Okay. It is long-term water quality impact assessment. So today I want to talk about assessment process or assessment technologies. Okay, my speech starts from the global climate change issues. Last week also I give some similar topics, but at the time I used some another case, urban cases, urban rural case. But today I want to talk about some long-term water quality change by climate changes. Global climate change causes the hydrologic component changes too. And also we have another, we need some assessment, watershed health assessment. Also we need some climate change vulnerability assessment. And also climate change adaptation practices. All these words is covers quite wide ranges, spatially and temporally. So what is driving force or source to identify long-term water quality changes? Okay. Land use, land cover change, or climate change is a methodological change, or geological issues. Yes, everybody has some different ideas, but I think this is all thing saying certain aspect of the climate change depend. Today, I saw some presentation that is RCP 8.5 scenario, and that is quite the meaning of this RCP 8.5, as you know, there is very big activities to develop environmental, no, not environmental, economic achievement. So this 8.5 scenario linked with very closely land use and land cover changes by spreading of the city areas. Based on some hydrology model, as you know, there is HSPF model that's used to analyze long-term water changes and also long-term water quality changes. This model used as an engine to calculate and simulate. Based on this model, I analyzed some changes, why, how they can connect. First, I'll talk about some watershed characterization and HSPF model structures. Because today's talking is just a talking to give some information and share with you. I use relatively small catchment areas, even I'm talking about long-term and huge global issues. I try to localize this issue to the middle-sized watershed. This is it has just 2,000 square kilometers area, not wide, but from the Korean land size, it is not small one, middle-sized watershed. So I use that one, and then already this watershed covered with the different kind of land use. Also, recently, last 10 years, intense development of urban areas, the area of urban spread out along to the road development. From this figure, you can see here, red part shows some urban areas. So here and there, My university located this here. Is this location far from the Seoul, about 100 kilometers south. And then I divide 1, 2, 3, 4, 5 sub catchment areas to analyze, to compare how much water quality change by the scenarios from change. This is simple schematic structure of the HSPF. Some of you already used, I think. So this is not the surface amount only, but also some water infiltrated solids, and also it stay up there and then delayed flow out, so river. Whole systems can be calculated, not only this one, spatially. It has some cover. Use this HSPF model, I simulate, calculate how much hydraulic component on this study areas change, like this. This is season, spring, summer, autumn, winter. Use 3 years data. Calculate and then analyze how much water is stored in the surface or on the ground or into flow. And also this shows some structure of the model applications. Here we collect metadata and model develop and then test file and get some try to get some how we can balance of our environment. This is example of the analysis. Flow and load duration curve used. This is very convenient. Okay, I'll explain a little bit. This shows some flow duration curve. This is one. This is Mr. Load duration. That means water quality changes. I collect data and then actually to have this here flow duration curve. As you know, I use some flow data and then I develop this line. This is percentile, like frequency, and this flow size. Here, this one is the low flow. That means flowing water is very small, and here high flow. And then this is water quality. I use some loading data. That means horizontal row can be calculated flow rate and concentrate. Here you see this is important. This line shows some. Actually, I use many data, but this line indicates. For example, every country or local government has some standard to control water quality. They have some kind of visuals. Okay, so this line show that kind of levels. Here I told concentration means the target or quality mandated by the government or some local. Okay? Using this one, and then we can compare. This is the standard level, and then it's over. That means this provides us some vulnerability of our quality management, something like that. So I use these two methodologies. This is the model structures. This is the calibration verification. I used our observed 8 years water data, rainfall data, water quality data to develop this model fit to our watershed analysis. Using this one, we set some climate scenarios and then compare some cases. Baseline and future. You calculate, use the RCP 5 to 8 scenarios. This is an example. Data set like this. These are all scenarios. Baseline. This last 8 years used to understand how much this land has some water and how much they can also effect on the local changes. And this is a 50-year later cases. That means long-term simulations using the model, that ideas. We have this standard baseline information. This one, this direction shows some economic development or some strategic changes and something like that. So this case is changed. Of course, not only rainfall intensity, but also land cover also changed. We simulate all things using different kinds of surface models. Yes, this one shows some scenario details. Simulate theory, calibration, verification, and up to the 2050. This part I calculate, use the model, use the rainfall, use everything. So I calculate this one, and then we try to how managing what is reason to change our water qualities after several 10 years. Compare his baseline with the future calculation. Yes, this is the result of the land curve changes and land use change map. We use another program, and then we develop this map using GIS. This present situation, and then this map shows some 30, 40 years later. Here, let's change it here. Okay. Let's change. As you know, the land curve changes cause some different pollution discharge changes. And also we have some meteorological climate change scenarios. It means water flow will be changed, gradually, location, patterns, and times. We calculate everything using this kind of methodologies, and we try assessment. What's main reason? Where is hotspot in huge time? That means this kind of information can be to make a strategy, long-term strategy to develop the city, and also to cover our environment. Yes, this is example rain precipitation scenarios. Here, height graph can be changed like this. Moving different. Okay? So this RCP 8.5 phase 1 means 2011 to 2020. This one baseline. This third phase here. Third phase is 20 years later, 40 years later, or something like that. This kind of things are prepared, and then using this, actually this rain precipitation intensity is basic data to calculate flow in the rivers, flow over the urban surface. All things can be calculated depending rain data and surface data. Both. Seasonal distribution of the future flow, that means water flow, unit is CMS in the one side. MHB side, DKK. Change how much compared to this baseline. Here, baseline, this color, this one, this one, this one, baseline. And then this is, okay, 85. This is gap, maximum, minimum. Phase 3, 1, 2, 3. This is phase 3. This is baseline, so this is phase 1, phase 2, phase 3. This is phase 3. From here, there. This is the barriers. Okay? This much water flow changed in this case, this time. And then this line, two lines, called this baseline areas. Okay? You can compare how much different. This one at one point, the small catchment. Already I told you my study area divide the 5 sub-catch areas. So this is one case. And this is another one, water quality, BOD data. To calculate this one, we collect many data observed from the riverside, also some data of the wash-off data from the catchment. Seasonal distribution, future BOD here. This baseline same, and phase 3 here, 1, 2, 3. You can compare how much difference here. And then this is BOD. Next one, suspended solid, total suspended solid. So origin of the BOD, pollution, and suspend. sorry. As you know, SS comes from some erosion, okay, or city surface by stormwater. But beauty, every day we discharge through the sewer. So sewer treatment plant is source to discharge BOD to the river system. So this kind of different sources. Okay? We capture this one, you can see, and then you have to compare this scale absolutely different with this one, ammonia or BOD. This is standard, and then we'll set this minus and plus thing. Okay, it's just one. But here 25 minus 25 times bigger and small, big gaps. Okay, that means SS's discharge is with some strong flowing powers. Okay? So different ranges. Ammonia, little bit very, and then this is PF4, but phosphorus. And then we try to use the data to identify where is source to discharge this kind of water pollution. Okay, in our water set, we calculate. So, and then on the GIS, we made map here. Water balance. That means previously I showed already water hydrologic component can change. This chart shows this water changes. Even this one shows some sudden time, but this kind of map calculate every day, every year. You can use all day and time and space. It was moved. You can compare this one. This is water, BOD, water quality. You have to keep this image and then compare this one. This is same water index, water quality indexes, but location. So this one and this one here change. Time by time, location by location, move. That means this result already reflects the change of land curves, of a change of hydraulic components, difference. Next is long-term water mass balance assessment. And again, I show some very similar graph. That is flow duration curve. Flow duration curve. This is for the baseline, and this is very active economic development of the pursuit. Okay, the case. We can compare people. This is percentage, low flow rate, more low. Gap is still, okay, it's low, still, gentle. So, difference. So, very interesting thing is, this time, at this present time, this high flow is very high, but in this case, okay, very low. And then based on this kind of data, these two data, we compare where the source of the pollutant, like this, in. And then BOD also, this is low duration time to let hope that this is for the road. Okay? Same. Okay, this is last scene. As you know, this is standard government or local government officials try to work hard to keep this much standard. But we need some another strategies. From the long-term view concept, we are prepared because over this line means we have very heavy vulnerabilities to keep water, not only water, but also some pollution control too. Thank you very much.
Thank you very much, Professor Han, for the next presentation. And for the next presentation, the next speaker, we have two more speakers. The first speaker is Dr. Pathan Banjongproo. He is working in the Department of the Drainage and the Sewage, Bangkok Metropolitan Administration, and he got a bachelor degree and master degree in the engineering from the Chulalongkorn University, and he got the doctor from the sanitary environment on canal water quality modeling from the University in Innsbruck in Austria. And he will present about the water quality management and wastewater tariff in Bangkok. And for the second speaker is the Thepnoo from the Bangkok Metropolitan Administration as well. Okay. For the speaker, the first one, Dr. Pathan Banjongproo. Please welcome.
Welcome to Bangkok. My name is Pathan Banjongproo from the Water Quality Management Division, Drainage and Sewerage Department from the Bangkok Metropolitan Administration. The authorities, the Bangkok Metropolitan Administration have the response for the treatment of wastewater, municipal wastewater. So today I was invited to talk to you about the water quality management, and also Mr. Kasame will speak the topic of wastewater tariff in city of Bangkok. To make the next slide.
อ๋ออาจารย์ใช้ตัวไหนก็ได้ค่ะ
ทำไหน
อันนี้ค่ะเรื่องสัตว์
Okay. That's good. Good. Okay. Next slide, please. Thank you. This is the laws and regulations that we have to follow. Mainly it was the Environmental Act and the Public Health Act. But the Building Control Act and the Metropolitan Organization Act is also very important. This tell you how the roadmap, how can you manage the wastewater in the city of Bangkok. This is our authorities, the Drainage and Sewerage Department. We are here in the This is the Water Quality Management Office. This is my office is here. We have others, the structural control, drainage system and canal system and the main drainage development and also the mechanical division. This is Bangkok. The city of Bangkok located at close to the floodplain, close to the mouth of the river, close to the seashore. So we have 1,500 square kilometers of area, but every day we consume about 2.5 million cubic meters of fresh water. So this water supply then is turned to the wastewater. So we have to collect them and to treat them. About 75% of wastewater is from the domestic use. So this is the situation of water quality in Bangkok. We take example from the canals and measure the water quality. So the black spot means the water quality is very poor. Still poor even today. So we do the master plan and we do the construction and the non-construction measures. So this is the map of Bangkok. This is the center area of Bangkok, which is densely populated with people, and then outside is green area, and you may see the yellow and orange area with the medium located urbanized. This is the master plan that has been written since many years. This is 1980s. At that time, people of Bangkok have no wastewater treatment plant, so we just start to write the first treatment plant in the center area of Bangkok. Then we developed to this plant in 1999, and this is the latest one in 1911. Was done by JICA, the Japanese authorities who help us to do the master plan. So, what is the treatment plant in Bangkok? This is the central and community and cluster and on-site. So the central and community wastewater belong to the municipality. The sizing of wastewater treatment plant in Bangkok. We follow the master plan, but the master plan was developed many times. The summarize is the sizing of the wastewater treatment plant in Bangkok is between 40,000 cubic meters per day to about 400,000 cubic meters per day. Because if we build a small treatment plant, we have to pay a lot for the treatment cost. But if we build too large size of wastewater treatment plant, then we have to pay a lot cost for the piping. So the city of Bangkok today have 8 wastewater treatment plant large size, which can treat about 40% of the total wastewater. So about 1 million cubic meters 1 million cubic meters a day that we can treat 45% of wastewater. Only 14% of total area, but we construct in the high density of population area. So, and this is what we do with the reused water. And this is the sludge. Our sludge, wastewater sludge, which is about less than 40 cubic meters per, less than 40 cubic ton, less than 40 cubic meters a day. It contains some heavy metal, so we not allow them to use with the edible crops, so we just apply them to the park. So this is the future project. We will construct more wastewater treatment plant in the city of Bangkok. About 669,000 cubic meters a day more. And this is a summary. This is about the cost, how much we have to pay for the treatment plant. This is the cost. Almost 40% of cost is electricity. You may see the maintenance is about 25 and the wages is 22. This kind of electricity is 30%, in some time it's almost more than 40. So what we have to pay for this electricity, half of electricity is pumping and another half is the aeration and the watering. Yes. So you may see this structure. This is the money that we have to invest for the wastewater treatment. And so it takes almost 30,000 baht per cubic meters per day that we can treat. What is the importance of community participation? Without the community participation, the project cannot going on. When we start to construct the wastewater treatment plant, not so many people want this kind of treatment plant to be close to their house. They just want, please don't bring it to our area. Just other area is better. Don't bring it to our area. We don't like it. So we have to do the activities with the community. Every project, before we start, we have to we have to do the community participation. We have to listen to the residents who live in that area. At least 2 times we have to do the community participation before we can launch the project. Allow them to share the ideas. What is yes, when we start to build a new project, the land acquisition is most of problems and also money. People don't like the wastewater treatment plant. They thought it smells not so good, so maybe they bring something not to their house. We don't like that, so we try to improve the design and the way how we can get the land. So most of land was from the Treasury Department, and we have to collect the wastewater fee. So Mr. Kasame will explain to you and we can discuss later. Maybe your chapel is very interesting because we have the effluent the effluent can be reused, but today we can reuse only 6%. We want to supply this effluent out to the consumer outside of the area. So maybe your charcoal may be helpful to reduce the nutrients in our effluent. Even it is not so much concentration, but I think we can do something because our flow is 1 million cubic meters per day. It is not a small amount. So Mr. Kasame will talk to you after. Thank you for your intervention.
ขออนุญาตครับ Good morning, everyone. Nice to see so many of you here. The topic of my talk is the wastewater tariff. In order to effectively implement a wastewater tariff, BMA must conclude 12 steps as follows. Wastewater tariff consists of organization, setting, legal concern, public relations, and technical works. Let me return to organization setting. That already Dr. Pathan already tell you about organization chart, but for data system and tariff we set up here under Water Quality Management Office under Department of Drainage. And then I would like to focus about legal concern. BMA ordinance, collection of wastewater tariff, and next notification about service area, rate of charge and invoice and payment. BMA set up and then let me give you brief about overview about progress of legal concern. BMA obtained approved BMA ordinance since 2004, and then 2 years later we proposed notification to the governor, but the governor did not approve the notification, but important for implementation of wastewater tariff because the governor thought that wastewater in water supply like this. They thought that wastewater should in the same bin or same invoice in water supply, and also support by National Environment Board. They agree that Metropolitan Water Works Authority should do this job, but MWA did not agree with them because they claim that it's against the act of MWA. Finally, wastewater tariff is free for 10 years until 2016. BMA Council revised BMA ordinance again. It means BMA Council come from National Council for Peace and Order. It means that we can find good things from dictator. And then this is the invoice of water supply. For the draft BMA ordinance collecting of wastewater tariff, First is about charge of building in service area, and it's a volume charge. It's 80% of water consumption, and then the rate of charge is depend on loading, and then about service fee and penalty. I will give you more about notification according to the ordinance. Consists of service area, rate of charge, invoice and payment, and about calculation about the building that use other sort of water, such as underground water, and the role and order about the building that has on treatment on site treatment plan, because they can, if they can treat effluent standard, meet the standard, they not pay for the tariff. For service area, Dr. Pathan already gave you about in the 8th treatment plan is cover 21 districts and to about 200 square kilometers. This is service area. We charge only in service area. And we propose about the rate of charge. We divide category in 3 categories. First is household. It's about what 80% of water supply is the rate of charge is 2 baht per cubic meter. And the second about the government sector office. Second one is about government sector, education, hospital or clinic. We charge 4 baht per cubic meter. And the last one is hotel, about industry or department store is a big building. We charge 8 cubic meter baht, 8 baht per cubic meter. And then I move to wastewater tariff management system. For this, they may have to set up and install computer system for building about invoice. First about database of polluter and invoice, and then about payment, and about accountant. This is BMA system overview for wastewater tariff. And the second one we should have about public relation for public involvement. About goal and objective, we should be designed to meet the needs of BMA and public. And next, about team and message, we have to promote cost-effective management of the public resource, and we have to commitment to protect public health and environment, and a target audience, program element and implementation work plan. We have ever survey about willing to pay wastewater tariff since 1997 under feasibility wastewater tariff projects. Number of population about 3,000. The target group willing to pay about 80%. And then under project of Basin wastewater treatment project in 2006, they're willing to pay about 60%. And in 2010, this is office already survey about wastewater tariff. The people willing to pay about 56, and then the last in Thonburi wastewater treatment project, the people willing to pay about 50%. and unwilling to pay about 44, and 6% no answer. And this I would like to show you about sewerage charge in Tokyo, because it's very expensive if compared with in Bangkok. They have this if use only less than 8 cubic meter is a fixed cost, and more than they have a second charge. If in people in Tokyo use 24 cubic meter, they have to charge about 2,000 yen. It's expensive than Bangkok. This is Melbourne. I would like to show you that in Melbourne they charge from the organization about wastewater and water supply. They in the same organization. That's why for the wastewater tariff is very easy, not difficult like in Bangkok, because we come from different organizations, BMA and FWA, different organizations. And in Melbourne they charge in the same bill, water supply and wastewater in the same bill. That is my staff design about wastewater tariff. We get data from MWA to estimate revenue. See this table. Taiwan, about the household, we have about 200,000 buildings, and this is water supply, 80% of water supply, and then the rate of charge is 2. We can give about 141 million per year. Thai 2, we got revenue about 500 million, and Thai 3, we can got about 100 million. This is total about 8 million per year. 800 million per year is can cover the cost and maintenance of wastewater operation, because Dr. Pathan already tell you about the cost of operation and maintenance, about 700 million per year. For the challenge of most area of Bangkok should be serviced by wastewater treatment facility according to the master plan. And in some criteria, on-site and community wastewater treatment system should be the alternative choice. Byproduct wastewater salad should be improved in quality, and collecting wastewater tariff should be put in the practice. Lesson learned. PPP or public-private partnership should be implemented for the future project. It can solve the financial problem, and collecting fee is another source of fund. Sorry. Okay, and next, people participation will play an important role to improve the surface water quality. And the last one, energy saving technology for wastewater system should be studied and applied for solving global warming. Thank you.